All right, today we're diving into what might just be the single most important staining technique in all of medicine, hematoxylin and eosin, or as you know it, H&E. It's the absolute bedrock of histopathology. That's the study of disease in our tissues. We're about to see how this incredible mix of chemistry and precision can take a colorless, nearly invisible piece of tissue and turn it into this vibrant, detailed map that's packed with diagnostic information. Now, at the very heart of this is what we call H&E morphology. It's the information the stain actually gives us, and it breaks down into three absolutely critical parts. First, it shows us the nuclei, giving us all these details about the cell's genetic command center. Second, you've got the cytoplasm, which tells us all about the cell's structure and what it does. And third, it lights up the extracellular matrix, which provides the context of all that connective tissue. Put them all together, and these three elements create the complete picture a pathologist needs to make a diagnosis. And this brings us to a really critical point about today's laboratories. You see, the quality of an H&E stain isn't just about making a pretty slide. No, it's a direct reflection of how much control that lab has over its analytical processes. A top-quality stain means top-quality control. Okay, so how does it all actually work? That brings us to this really elegant interaction between the dyes and the tissue. You can think of it as a kind of ionic dance, all governed by the simple laws of electrostatic attraction. It really all boils down to one simple principle: opposites attract. The hematoxylin complex is what we call cationic, meaning it carries a positive charge. So it's naturally drawn to the anionic, or negatively charged parts of the cell, and that's mainly the DNA and RNA. On the flip side, eosin is anionic, with a negative charge. It binds to the cationic, or positively charged proteins you find in the cytoplasm and collagen. This fundamental attraction, positive to negative, is exactly what creates that iconic color contrast we see in H&E. So let's zoom in on our first dye. Now here's something you might find pretty fascinating. The stuff they get from the logwood tree, it's not actually a dye yet. It's a precursor. In its raw form, it can't stain a thing. It has to go through a chemical transformation to actually become useful. And this transformation happens in a couple of key steps. First, through oxidation, that precursor, hematoxylin, gets converted into hematine, which is the active dye. But hang on, it's still not ready. In step 2, mordanting, the hematine gets combined with a metal salt. Think of the mordant like a bridge, something that allows the dye to get a firm grip on the tissue. This creates the final dye complex. And it's this big, positively charged complex that, in the third step, can finally bind to those negative phosphate groups inside the nucleus. Without that mordant, the dye just can't attach. Simple as that. But wait, there's one last chemical trick up its sleeve. You see, after the initial staining, the nucleus is kind of reddish, and the dye is still soluble, meaning it could wash out. So the bluing reaction introduces this critical pH shift using a weak alkaline solution. And this simple change converts that soluble red complex into an insoluble, crisp blue form. I mean, look at the before and after here. You can see the dramatic difference it makes. This step literally locks in the color and gives us that sharp, clear nuclear detail that is so essential for a diagnosis. Okay, now for the counter stain, eosin. Its chemistry is just as precise, and for eosin, it all comes down to pH. It has this Goldilocks zone where the pH has to be just right. If the solution is too alkaline, the staining is weak, washed out. If it's too acidic, you get this muddy, overstained mess. The sweet spot, the optimal zone for perfect contrast, is this really narrow window between pH 4.5 and 5.0. And keeping it in that range is absolutely critical for highlighting the cytoplasm, the proteins, and the collagen in just the right way. So, with all that chemistry in mind, how does this come together in a practical day-to-day process? Well, let's look at the 10-station workflow. And this isn't just a random list of steps. It's more like a precise choreography, where every single station has a vital part to play. The workflow always starts with preparation. First up, deparaffinization, where xylane is used to melt away the paraffin wax that the tissue is embedded in. Next is rehydration. The tissue moves through a series of alcohols to gradually reintroduce water. Why? Because our dyes are water-based. The third station is our first big staining step, applying the hematoxylin for about 5 to 10 minutes to get those nuclei colored. And finally, a simple water rinse gets rid of any excess dye before we move on. Now, the second half of the workflow is all about refining the stain and finalizing the slide.
It kicks off with differentiation, a super important step we're going to focus on in just a second. Next is bluing, that crucial pH shift we talked about to lock in the nuclear color. Then comes the eosin counterstain to add that vital pink contrast. After that, we basically reverse the process. Dehydration takes all the water back out, clearing with xylane makes the tissue transparent, and finally, mounting with a cover slip creates that permanent slide that's ready for the microscope.
Okay, let's circle back to Station 5, because this is, without a doubt, the most important moment of active control in this whole process: differentiation. It uses a weak acid to wash away any extra hematoxylin that's just kind of clinging to the background. It's all about achieving the perfect signal-to-noise ratio. You're refining the stain, making sure only the nuclei, the signal, stays sharp and clear, while all that background, the noise, is silenced. The final clarity of the nuclear detail is decided right here, in this step. This is the very definition of a critical control point.
And that leads us perfectly into our next section. Now that we know the chemistry and the process, what are we actually aiming for? What does a perfect stain even look like, and what are the common hurdles that can get in the way?
So what is the target? Well, you can think of it as the color palette of pathology. A perfect stain has these crisp, sharp blue or purple nuclei, where you can actually see the internal chromatin patterns. The cytoplasm should have different shades of pink. Collagen needs to be a distinct pale pink, and you want to see red blood cells as a vibrant, bright red-orange. The key things to look for: sharp nuclear chromatin, clear cytoplasmic differentiation, and absolutely no background haze. But, getting that perfect stain isn't always possible. And this quote right here highlights the single biggest reason why. It's a fundamental law of histopathology. The staining process can only work with the material you give it. If that tissue wasn't properly preserved right at the very beginning, no amount of skill or fancy technique in the staining process can ever fix it. Think of these uncorrectable issues like a pyramid. At the very bottom, the foundation is fixation. It has to be done right to stop the tissue from decaying. Next up the pyramid are the tissue's dimensions. A section that's too thick just won't stain correctly. And at the top is processing, making sure all the dehydration and clearing is done right. An error at any of these pre-analytical stages, right at the start, is going to compromise the final result. You just can't fix poorly preserved tissue later on. The good news is, a lot of errors are correctable. We can actually diagnose the stain itself. So for example, if you're seeing pale nuclei, the likely culprit is that the hematoxylin is exhausted. The fix? Replace the dye. If the slide looks kind of muddy, that probably points to over-differentiation, so you'd cut back on the acid exposure time. Weak eosin staining? That's a huge clue that the pH is too high and needs to be brought back down to its Goldilocks zone. And if you see patchy staining, that often means the wax wasn't removed properly at the start, so it's time to change out the xylene.
All right, finally, let's bring this all into the context of a modern accredited lab. This is what takes H&E staining from just being a technique to being a fully validated diagnostic method, one that's governed by strict scientific protocols, safety rules, and international standards.
Yeah, this is far from a set it and forget it kind of thing. Every single day involves rigorous quality control. That means running a control tissue to make sure the stain is working perfectly. It means visually checking the quality of the nuclear and cytoplasmic detail on that control. It means constantly monitoring the status of every single reagent and its pH. And it means analyzing trends over time to catch any drop in quality before it could ever affect a real patient slide. And this daily QC, it all fits into a much bigger framework: ISO 15189 compliance. That's the international gold standard for quality in medical labs. And it's built on this cycle of continuous improvement. This cycle includes things like proactive risk assessment, constant validation of all your procedures, thorough documentation of absolutely everything, and regular competency training for the staff. Under this standard, a failure in staining quality is a major problem because it can lead directly to a diagnostic error. So let's bring it all home. The H&E method really stands on three core pillars. First, the chemistry. It's an ionic process that absolutely depends on oxidation, mordants, and precise pH control. Second, the process. It's a super sensitive workflow where variables like fixation right at the beginning and differentiation in the middle are critical. And third, compliance. It's a controlled method that demands daily QC, validation, and meticulous documentation to meet the highest possible standards.